let's look at a common type of quartic function and explore the relationship between the x-intercepts, local minimum, and inflection points. We're given the function f of x equals ax to the fourth power plus bx cubed, where both a and b are positive constants. This function can also be factored as f of x equals x cubed times the quantity ax plus b. Although you could sketch this graph directly by using its x-intercepts, let's instead start by analyzing its derivative. First, we take the derivative of f. The first derivative is f prime of x equals 4, ax cubed plus 3bx squared. We can factor this as x squared times the quantity 4, ax plus 3b. Now we set f prime equal to 0. That gives us two critical points, x equals 0 and x equals negative 3b over 4a. Next, we analyze the sign of the derivative. When x is less than negative 3b over 4a, the derivative is negative, so the function is decreasing. Between negative 3b over 4a and 0, the derivative is positive, so the function is increasing. And when x is greater than 0, the derivative is still positive, so the function continues to increase. This tells us that there is a local minimum at x equals negative 3b over 4a, since the derivative changes from negative to positive at that point. At x equals 0, the derivative is 0, but since it does not change sign, there is no local maximum or minimum there. Let's now move on to the second derivative. Taking the derivative of f prime, we get f double prime of x equals 12 ax squared plus 6bx, which factors as 6x times the quantity, 2ax plus b. We set f double prime equal to 0 and find two possible inflection points, x equals 0 and x equals negative b over 2a, which is the same as negative 2b over 4a. Now, let's look at the key x values we've found so far. We have an x-intercept at x equals negative b over a. A local minimum at x equals negative 3b over 4a. An inflection point at x equals negative 2b over 4a. And another inflection point, an x-intercept at x equals 0. To better compare these, we express all of them using a common denominator. That gives us negative 4b over 4a, negative 3b over 4a, negative 2b over 4a, and 0. So the x values in order are negative 4, negative 3, negative 2, and 0, measured in units of b over 4a. If we look at the spacing between these points, we see a simple pattern. The distances between the inflection point, the local minimum, and the intercepts follow a consistent ratio of 2 to 1 to 1. What's important is that this pattern stays the same even if the signs of a and b are reversed. This type of spacing and symmetry is common in quartic functions and is useful when sketching graphs or solving calculus problems, especially on tests like the SAT or in advanced high school math.